Howdy, ladies and gentlemen. We're going to talk about solution formations and solubility curves today, as well as solubility of gases. The article that I have here actually is talking about a day in Deseta, Texas, and it started like any other day, but ended up very differently. Over the period of a few hours, an area of land that literally was the size of two football fields. So think about um, our football field and our stadium, and think about um, two of those size of land, about that size, collapsed. No one was injured, no homes really suffered any damages, but a few vehicles and pieces of equipment fell into the hole in the ground. And the hole was literally known as what a sinkhole. And a lot of y'all have seen these on TV and certain like 911 episodes and things like that, or you have heard about it before. And so it frightened a lot of the residents, and they were concerned that it might continue to grow. Really, they are very common in eastern Texas, where there are geological formations known as salt domes, which lie underground. Those salt domes are natural deposits of really just sodium chloride. And that raises the question, why are salt dome areas prone to sinkholes? Well, if you think about it, salt dissolves in water really well. So when you think about that, there's different things that will influence the rate of dissolution, which means dissolving of salts. And I want you to think about how these factors relate to maybe this sinkhole formation. And then we could come back and talk about it later. All right. Let me see if I can get my clicker to do what it's supposed to do. Oh, that's not what I wanted to do, but that's okay. We'll just keep going. All right. Factors affecting rate of solution. Okay. There are three of these, and they are in your notes. You need to make sure that you make note of them. All right. So, really, the way to think about this is when you're thinking about dissolving things in a solution or a solvent and creating a solution, what are some things that make it dissolve faster? Okay. So one of them is agitation, and agitation would just mean that you're moving it around. It could be that you shake it, you stir it, those kind of things, but it brings fresh solvent into contact with the solute. It doesn't affect the amount that will dissolve, it just makes it to where it'll dissolve quicker. So this is why we stir our iced tea when we put sugar in it, is so that we can get that agitation, so that we can bring that fresh solvent into contact with the solute. Temperature is another big factor. Heat actually increases the rate of um, that a solution will dissolve. So by increasing the kinetic energy of the solution and the motion of the particles, it'll make it to where it will dissolve faster because they'll bump into each other. The solvent and solute will more often. It also affects how much will actually dissolve, and we'll talk about that in a little while, but it will affect how much will dissolve in it. If any of you have ever had sweet tea from Chicken Express, they actually put all the sugar in their tea when it's actually really warm. So it will hold more sugar in it when it actually cools down. So that's one thing to think about. And then the third one would be particle size. And particle size just has to do with how big are the particles. Smaller particles will obviously dissolve faster because they have a greater surface area. And if you think about it, when you think about sugar versus your artificial sweeteners. Sorry, I lost my word. Um, the artificial sweeteners are more grainy and they're smaller pieces, so they actually seem to dissolve faster than regular sugar crystals will. If you think about it, we also gave you these antacids in a previous lab before, and we gave you pieces of them. And so, depending on how quickly or how small your piece was, by breaking them up, we actually caused them to go into solution quicker. So which would dissolve faster and why? Okay, we've got a cube of sugar, we've got granulated sugar, and we've got powdered sugar. So this would be where I would say to pause the video for just a sec and go ahead and talk to your table mates about what you believe would dissolve faster and why, thinking about what we just talked about. Okay, hopefully you did talk to your table mates regarding that information. And so when you talk about it, um, what were the thought processes in the room? Somebody should be able to tell me what that is. Hopefully someone did say powdered sugar would dissolve faster. And if you had to put them in order, it would be the powdered sugar first, then the granulated sugar, and then the cube of sugar. But why would be the question? And that would be typically related to um, our reason number 3 for their particle size, as well as because you have more surface area on the powdered sugar versus the granulated sugar even. And then the cube of sugar, you just have the outside, and so it has to break it down so it can get to the inside. So all right, so now we're going to talk a lot about solubility. And solubility is really the measure of the amount of solute that will dissolve in a given amount of solvent. All right, so when you're thinking about this, I would highlight in your notes that it is the amount of solute in a given amount of solvent. Now, we are normally going to talk about it in grams of solute for 100 grams of solvent. All right. You guys don't really use your textbooks, so we wouldn't have the solubility charts, but we do have one in your notes right here that we're going to discuss. Okay. So notice um, we have grams of solute per 100 grams of water. And so when we talk about solubility, we always talk about the temperature. So to read this table, you find the temperature of your solution or you find the concentration of your solution, either one. Okay, so if you're going to use temperature, then you're using the x-axis. If you're using the concentration, then you're going to use the y-axis. Okay, then what you do is you trace over to the other axis, and wherever they meet, that's the corresponding value for solubility on the line. Okay, so for example, if I wanted to talk about 50 degrees and I wanted to talk about ammonium chloride, okay, this is ammonium chloride NH4Cl, and I said it was at 50 degrees Celsius, and I wanted to know what my concentration would dissolve there, what was my solubility. Well, I would go up to 50 until it hit the line, and then I would go over, and that would tell me that 50 grams of ammonium chloride would dissolve in every 100 grams of water. So that's pretty simple. And so solubility with these always is about the temperature. So if I wanted to say, okay, instead, let's say that I have, let me go over here and change what I have. Let me do red. So if I said that I wanted to look at sodium nitrate, which is this one right here, okay, and I wanted to say that I wanted to know what temperature, um, let's say 140 would dissolve at. So I would go up here to 140 and I would hit the line for that particular compound, and then I'd go down, and that would be about 75 degrees Celsius. So that would be the temperature where I could get 140 grams of sodium nitrate to go ahead and dissolve for every 100 grams of water that I had. Okay. So when we're talking about solubility of solids, and this is just something that you can kind of write around it or near it. I think it might be a little bit below it as well in your notes. But most solids become more soluble at higher temperatures. Okay, so you'll notice that as our temperatures go around here, okay, so they become more soluble, higher temperatures, and this is solids. That's really important to understand too, that this is for our solids, okay. If you look at this solubility chart, most all these curves go up. The only two that don't are sodium sulfate and cerium sulfate. Okay, so the sulfate compounds don't seem to go up. They don't follow the normal trend. But most of them are more soluble the higher the temperature goes, which was a factor that we talked about earlier as well. So we can also use these graphs in an interesting way. And this question I don't think is on your notes, but this is something that you need to be able to do for your classwork. So what mass of sodium nitrate can be dissolved in 250 grams of water at 20 degrees Celsius? So sodium nitrate is the one we were talking about earlier. So that's this one. And we're going to go to 20 degrees and we're going to go up and it hits right about there. Okay. And so then we could go across. And I think I ended up using 90 here, even though that's probably not quite 90, but we could say 90. All right. And so remember that this 90 is for 100 grams of water, right? We want to know about 250 grams of water. So in order to do this type of problem, you just set up a proportion because we can figure out that we know that it's 90 for every 100. So it would be x over 250. So you could cross multiply, then divide, and you would end up coming up with a value of 225 grams of sodium nitrate will dissolve at 20 degrees Celsius in 250 grams of water. So that's another way that you can just set up a proportionality looking at these solubility charts. And that's something, like I said, that you're going to have to be able to do in your classwork. So you should be able to do that. All right. Then we have gases. Now, gases are always less soluble at higher temperatures. So that's important to understand. Less soluble, higher temperatures. And this actually is written down in your notes as well. So this is talking about gases specifically. Notice all these curves, as the temperature goes up, they go down. And this is also why when you have your sodas, when they're warmer, the gas won't stay in solution. It'll start to bubble out and your actual soda drinks will go flat faster because the gases are less soluble if they're hot versus when they're cold. When they're colder at lower temperatures, they'll hold that solubility better, so they won't all bubble out because they'll stay in solution. Okay. So again, factors that affecting solubility would be pressure also. Pressure for solutions of gases is really important when you're pushing those gases into the liquid. So if you're increasing the pressure, you increase the solubility. So increasing pressure increases solubility. And we have to remember we are talking about a gas. Okay, so pressure for solutions is really important. And that's actually how they get your carbonation into your sodas, is they actually put it under pressure. That's why when you let it off of, like when you open the container or your can and it makes that noise, that has to do with the fact that you're releasing pressure. And so then it comes out of solution more, and that's when it starts to bubble. Okay. Now, Henry's law says that at any given temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. So that's really important because it's very much like what we did with gas laws. So the direct proportionality is S1 for solubility 1 over pressure 1 equals solubility 2 over pressure 2. It is of the pressure above the liquid, and that's why when you lower the pressure by opening the container, you lower the solubility as well because they are directly proportional. And that's why more of your solutions come out of, that's why more of your gas comes out of solution. It won't stay in solution. So at 25 degrees Celsius, the solubility of a certain gas in water is 0.75 grams per liter at a pressure of 1 atmosphere. So what is the solubility of this same gas if now I change the pressure to be 10 atmospheres? So I'm keeping the temperature the same, so that's not a factor in this question, but it does just give you that value. So we have to first identify our variables, which would be our S1 equals 0.75 grams per liter, our P1 equals 1 atmosphere, our S2 equals what we're trying to find, our solubility, and then our P2 equals 10 atmospheres. If we're using Henry's law, which is S1 over P1 equals S2 over P2, okay? If you remember, when I did gas laws, I really liked for y'all to not have these fractions, and I liked it to be more that y'all had S1 P2 equals S2 P1, and that was just doing that cross multiplication already, okay? And so if that's the case, then I'm going to fill in my 0.75 milligrams per liter. I'm then going to multiply by my pressure 2, which is my 10 atmospheres. And then I'm going to divide, because the opposite of multiplication is division, with my P1, which is 1 atmosphere. And that would have me solve for my S2. Okay, so cross multiply, then divide, which is the same thing that I have shown over to the side. And then I'm allowed to have two significant digits because of my 0.75 and my 1.0. So my answer should be 7.5 grams per liter. So then that would be my answer. That's my new solubility. Okay. So I believe we have one more question in this section that we'll do today, and that is pressurized CO2 is pumped into 3 cans of soda. The first can is at 10 degrees Celsius. The second is at 20 degrees Celsius. And the third is at 50 degrees Celsius. In which can will the most gas dissolve, and why? Pause the video now, talk to your table mates, and then come back and we'll discuss it. All right, hopefully you've had enough time to discuss the question with your table mates and come up with a reason for why. Not only which one, but also the why is really, really important. So, which one did you think it is? The first can, the second, or the third? Well, we did talk about factors that affected solubility of a gas in a liquid. And one of those was that the temperatures had to be, the lower the temperature, the more soluble they would dissolve, or the less the gas would dissolve in. The higher the temperature, the less the gas would dissolve in. That's why we made the comment about why we keep our Cokes and things like that cold, is so that the gas will stay in solution longer. So the actual one that will hold the most gas will be the first can because it's at 10 degrees Celsius and it's the lowest temperature. So it'll hold the most actual gas in its solution. All right. You guys have a good one.